So vapor pressure, what is it? So vapor pressure is where the gas exists above the liquid. And we did talk about this before, but in this picture, you see a pretty good example of what vapor pressure might be. So on the left side, you see the liquid ethanol. Now, all liquids have some vapor pressure, and the vapor pressure itself is dependent on a couple of things. It's dependent on the atmospheric pressure, and then ultimately what liquid it is. So every liquid has its own unique vapor pressure. And now so in this example, they're just looking at liquid ethanol. Ethanol evaporates very quickly. All right, and you know this because if you've ever been near someone that's drank alcohol, you know it because they smell like it, because their body it's basically exiting your body in the form of a gas, and you smell it. Now, vapor pressure is actually what happens above the surface of the liquid, so in this region here. So when you don't have any gases present, the vapor pressure is zero. But that's not necessarily going to be true because all liquids have some vapor pressure. So what happens over time is that in this flask, these ethanol molecules that are down here will start to vaporize into the space above, and they'll start to fill this space, and they'll continue to fill this space until they reach what is called equilibrium. Once they reach equilibrium, that then represents the vapor pressure. All right, so we call this dynamic equilibrium specifically. So what happens at dynamic equilibrium is these gas molecules that are above the surface of the liquid, what they do is they go into the liquid and they come out as a gas. And they do this equally, all right, proportionally. As one comes out, the other one goes in, because there's no more room for more gas molecules to come out. That represents the vapor pressure. Now, in your textbook, in the appendix of your textbook, you're going to find a table for water's vapor pressure at differing temperatures. So you say, well, why is that important? Because you have to know the temperature that you're working at, and you also need to make sure you know what the vapor pressure is at that temperature. So as we start to change the temperature, you're going to change the kinetic energies of the molecules. The higher the temperature, the greater the kinetic energy, the higher the vapor pressure. That's something you ought to write down. So the greater the kinetic energy, well, let me start over. The higher the temperature, the greater the kinetic energy, the higher the vapor pressure. All those tie together. So temperature is a key component in this vapor pressure discussion. So it's a very important detail to know what the temperature is. Has everyone got this stuff wrote down? Y'all finished? All right, so the boiling point of a liquid is the temperature at which its vapor pressure equals the atmospheric pressure. Now, what exactly does this mean? What this means is that if you change the atmospheric pressure, you are going to change essentially the boiling point of that substance because its vapor pressure is now different. So we live near Jamestown, North Carolina. Jamestown's about 850 feet in elevation. our boiling point is not going to be exactly 100 degrees Celsius because our pressure, our elevation isn't at sea level. So we kind of base this around sea level. So if you go down to the beach, so at the beach, you're at 0 feet in elevation because you're at the beach, you're at sea level. You would expect your boiling point to be right around 100 because of how the atmospheric pressure is. As you guys go up, and you probably have experienced this before, as you go up in elevation, what happens to your eardrums and your ears? What do you do? What do you experience? Well, most of you experience the popping that you feel as you go higher in elevation. Now, as you go higher in elevation, you all are also changing the atmospheric pressure. That's why your ears pop, by the way. At the same time, you're changing the physical properties of the liquids as well. So at higher elevations, you're going to result into a lower vapor pressure, and a lower vapor pressure results in a lower boiling point. So water, if we look right here on the graph, water at 760 torr, now this is also 760 millimeters of mercury. So 760 millimeters of mercury is also equal to 1 atmosphere. So this goes back to your gases that we talked about last semester. So 760, 1 atmosphere, that's your baseline. At 760, you're at 0 feet elevation, so you're at sea level. So at that particular pressure, your boiling point is 100 degrees Celsius, and you come straight down to the x-axis here and find that. Now, let's say that you go up to the top of Mount Everest. Mount Everest is what, 30,000 feet up in elevation, and so let's say that they measure the pressure of 600 millimeters of mercury there. So, and we asked the question, okay, what's the vapor pressure? What's the boiling point of water going to be there? So it comes straight over and comes straight down. So what we see here is the boiling point for water at 600 millimeters of mercury is roughly about, I don't say 90 to 92 degrees Celsius, just estimating it here. So it could be 95. No, that's probably about 90, 92. So now the other liquids see the same trend. All right, so you have ethanol, which is lower boiling point at normal pressure, and then diethyl ether, which is normal, but 34.6. It did. So if you guys were in lab this week, which y'all were, I don't think y'all were. No, that was this Wednesday, people. So for those that are going to be in lab Monday, you'll get to experience the ether part. I'll save that for you till then. I won't spoil it for you. So again, this graph here represents the vapor pressures and the different temperatures at which the boiling points will take place. Any questions on that before I get started with phase diagrams? Are y'all still there? Y'all are being really quiet today. I don't like that. All right, keep in mind I can't see the chat box when I'm looking at the PowerPoint. So if y'all comment, just turn your microphone and say, yes, I understand, or have a question or whatever, please. All right, so phase diagrams. What is a phase diagram? Phase diagrams display the state of a substance at various pressures and temperatures in the places where equilibrium exists between phases. So in a nutshell, phase diagrams help us determine the physical properties of substances at different pressures and temperatures. So, general outline of a phase diagram is found in this picture here. So, what I'm actually going to do is I'm going to go to a different source because I like to do my own little thing here with phase diagrams. So, what can we get from a phase diagram? What information? So the first thing is let's just draw a phase diagram. So pressure and temperature. The first thing you have to do is you have to understand the different parts of it. The basic outline of a phase diagram looks like this. This is just a generic phase diagram. They change depending on the liquid. So if your temperature is super cold, well, a cold temperature is typically going to yield a solid. So your solid starts off, and then as you start to warm up the temperature, your solid melts into a liquid. And if you keep heating up your liquid, eventually your liquid turns into a gas. It will vaporize into a gas. Now you can go backwards. If you cool it down, your gas will turn into a liquid by condensing. And then your liquid will turn back into a solid by freezing. So those are the basic pathways. Now there's two other ones that we haven't looked at, and that's going from a solid to a gas and a gas back into a solid. So a solid turning into a gas is called sublimation, and then a gas turns back into a solid is called deposition. We talked about those the other day. So what I want you guys to really focus on here are these lines that you see here. These lines are representing the freezing point. It also represents the freezing melting point are the same. It represents the boiling point, and it also represents the sublimation point. But we don't really focus on sublimation too much in here because we don't really ever see it. The only time you might see sublimation is when you have dry ice. So if you were to set a block of dry ice on the tabletop, all right, what you would see coming off are the gas molecules going straight from a solid to a gas. So one thing that you never see with dry ice, so dry ice again, keep in mind that is CO2. So you'll never see a liquid form from dry ice because it doesn't go through the liquid phase. It goes straight from a solid to a gas. So that's a good example of the sublimation. Now another one that you probably may or may not have experienced, if you go into an elder person's house, a lot of times they have this really distinct smell coming from their bedroom, their closets. And so what they typically do is they put these little round balls in their closets. These little round balls are called mothballs, and they smell. It's not a very pleasant smell. Now what that actually is naphthalene. And naphthalene does not turn into a liquid, and that's why you smell it so strong. What that does is it keeps all the moths out of the closet from laying eggs on their clothes. So naphthalene does the same thing as dry ice. It will sublime and turn to a gas over time. And eventually the mothballs will disappear, but they don't smell good. That's one thing I hated about the mothballs, is they stink. So now for the others, you guys have experienced these here. You've experienced this with water. You've experienced this with alcohols, especially in the lab. So you've seen these. Now, there's other parts to the phase diagram that I want to discuss here, right? So the next one is this midpoint right here, right? So that midpoint is called a triple point. All right, so this is called a triple point. So a triple point is when you have three phases intersecting each other. All right, so three phases intersecting or coming together. So here we have our solid, our liquid, and our gas phase coming together to form that one triple point. Now the other one that you're going to see is found up here. Now this one is called the critical point. And the critical point is where this you cannot distinguish between a liquid or a gas. So cannot distinguish between a liquid or gas. So we have a special name that we call that. We call this a supercritical fluid. So that's what that's called, is a supercritical fluid. So on a phase diagram, there is only one critical point, and that's always occurs between the liquid and the gas. And sometimes there may not be a critical point. On this phase diagram, there is. Now, as far as the triple point goes, you might say, well, there's only one triple point. That's not necessarily true, because it really depends on the substance that you're looking at. So water is a great example. Water is a very unique substance because it has multiple solid point phases. So I'm going to go to, let's see if I can go to Google here. We're going to look at the phase diagram of water. Oh, here it is. All right, so when you look at the phase diagram for water here, what we see, and I'm going to try to make this where we can see it easily here. So we see our solid, we see our liquid, and we see our gas. That's normal. Here we have our first triple point, which is what we expect. It's where the solid and the liquid and the gas come together. We just saw that in the previous one. Now, as you look closer at this phase diagram, what we see, and I want to get close in on this, is that you see these little circles here. These circles that you're seeing here are representing other triple points. So in this phase diagram, you have one main triple point. You have, let's see here, 2, 3, 2, 3, 4, 5, 6, 7, 8, 9. So on this particular phase diagram, we have 9 triple points for the phase diagram of water. Now that's for this phase diagram. And so these, yes, the blue colored phases are all solids, but each solid is unique in its own way. And so, in fact, I missed one right here. So there's another phase diagram there, or a triple point. So that makes actually 10 triple points. So, so there's multiple solid phases, and they're all unique. Because what happens here is, if you look, this is representing the pressure. Now the temperature for these, until you get higher up, different. So, but for the temperature, the main part is that once you go up at this 0 degrees Celsius, you see that these solids all exist around the same temperature and below. So keep in mind that pressure has a really drastic effect on the way a substance interacts with the environment. So if you take a pressure and you start squeezing on the liquid water, what will happen is that you start to conform it and you force it into this solid. Now temperature helps speed that up because you're lowering the kinetic energy. So as you start to squeeze on that solid, those atoms, keep in mind that when you look at a solid form of water, it actually excuse me, it actually has a hexagonal structure to it. So there's a lot of space in the middle of this structure. And so each one of these corners will represent a water molecule or atom combining. These are your intermolecular forces that are at play here. So if you squeeze on this, well, there's plenty of room for it to compress and make a different structure. And the tighter you squeeze, the more pressure you're going to put onto that structure, and so it's got to conform. It's just like a garbage compactor. If you take your garbage and you put it in there, your garbage has its own unique shape. But as soon as you press that button and you start increasing the pressure, you start changing the form and the shape of your garbage. And eventually you squeeze all that garbage together to make more room. And so the same thing's happening here, is that as the pressure increases, those water molecules are compressing and being squeezed, and they're going to conform to different solid structures. That's why we have different solid phases. Now that's not observed in a liquid or gas because they're not interacting with the pressure like the solid phase would be. So liquids are there's just one liquid phase, and it's going to be one gas phase. Now also on this same phase diagram, you can see there's a critical point found here. All right, and so there's your critical point. Once you go past the critical point, you then are known as a supercritical fluid. So that's an example of another phase diagram. That's a very elaborate one involving water. So let's look at some of the ones that the PowerPoint has. So now the PowerPoint does look at water again, and what you want to do and the reason why it's looking at water is because of this trend here. So there's a backwards trend. So typically when you have a phase diagram, you have a forward trend like this. So this melting point, freezing point phase, if you look at water, it's actually backwards. And one of the things we have to pay attention to is the fact that we look at the density of water versus solid water. So liquid water's density is right around 1 gram per milliliter, and solid water is less than 1. That's why when we look at ice floats on top of water, and we see that show up within the phase diagram. So this has to deal with the way water interacts with itself in between the phases and its density. And you can see the point here that the PowerPoint has made about that trend that you see here. Any questions on this? Does anyone have any questions in general? If you do, turn your mic on and ask me. I can't see your chat box. All right. You are a quiet group today. So next phase diagram is for CO2. So CO2 is unique because we talked about dry ice earlier. If you take dry ice and you put it on your table, the dry ice sublimes and turns from a solid to a gas. So your table is your room pressure, our atmospheric pressure is right around 1 atmosphere. So if you look at the temperature scale here, so we're roughly around 25 degrees Celsius. Dry ice at 1 atmosphere is going to be below this temperature here. So let's say that your dry ice is here and our point is here. So this represents your normal temperature roughly. So as you look at this, so when it's in the freezer, the temperature is really cold. As soon as you take it out of the freezer, the temperature is going to go from, let's say, minus 80 to 25 degrees Celsius. So when you touch dry ice, really what you're touching, the temperature of that substance is minus 78.5 degrees Celsius. Now, I know you've all picked up an ice cube. Now, here's what I want you to do. I want you to take that ice cube. I want you to hold it in your hand and don't let it down on the ground or set it on the table. Hold it in your hand. How long will you hold that ice cube in your hand before you have to let it down? So another phase diagram. So this phase diagram is a little bit more involved than the CO2 was, but you still see, all right, so this is phase diagram of carbon, first of all. And carbon has two solid phases, graphite and diamond. It also has a liquid phase and it has a gas phase. So what I want you to understand here, and I want you to see here, is that there are two triple points found in this phase diagram. All right, there are two solids, and this is the part that I like to teach students because you may or may not know this, but diamonds, there's an old commercial that says diamonds last forever. And I know that some of you have probably heard of that. But there's a lot of false information given to you in that commercial because actually diamonds do not last forever. Diamonds form under high pressure and high heat. We live on our surface. Up here on top, there's low pressure and there's low temperature. So what happens is the diamond substance, the solid diamond, eventually loses and goes down in pressure and converts from a diamond into graphite. So your diamond ring that you might end up getting if you're engaged, or you might give to your fiance, whoever that is, that diamond that you give to them eventually will convert into graphite. And so that diamond that you give them is one of the hardest substances on earth. That's what we use to cut all of our tabletops out, the granite countertops, marble countertops. And over time, that diamond will turn into graphite. Graphite is so soft that you write with it with a pencil. That's what's actually in your pencil is graphite. Graphite's super soft. So this phase diagram illustrates the differences between the two solids. It shows you that it still has a liquid and a gas phase. Now these other phases that you see in here, these are nothing that you have to worry about. So we'll cross them off. So don't worry about them. Our main focus is what's circled here. the diamond, the graphite, the liquid, and the vapor.